All right, let's work on another LeetCode problem. So our second problem of the day is LeetCode number 300, longest increasing subsequence. Given an integer array nums, return the length of the longest strictly increasing subsequence. A subsequence is a sequence that can be derived from an array by deleting some or no elements without changing the order. And can you come up with an algorithm that runs in O of n log n time complexity? N log n, huh? Interesting. So, my initial thoughts for so this problem seems familiar, I guess. I think traditionally this is solved with dynamic programming. So what you do is that each element has two subproblems. We either start the sequence at our current number, or we continue our subsequence from a previous number, which is for all elements prior. And then that let's see. If we did that, then we would have probably an O of n squared runtime, because we'd be checking 1, then 2, then 3, and so on and so forth, up to n minus 1 comparisons, or n minus 1 numbers, I guess. And that comparison would be if the number itself is less than current number, and chain size at number is greater than max so far. So we'd get the maximum of the chain at that point. So that's where the dynamic programming part comes from. What if we wanted to do it in O of n log n time? Well, we don't want to change the order of the remaining elements. Which probably means no sorting, which I think is a very curious problem. Well, does it mean no sorting? Because, for example, if we start with 0, 1, 0, 3, 2, 3, suppose we swap the 0 and 1 to get 0, 0, 1, 3, 2, 3. The subsequences don't really change, do they? If we wanted to do a subsequence like 0, 0, 0, 3, it still exists. We just delete the element later. But I guess the problem is that if we wanted to do like 0, 1, 0, this subsequence no longer exists, right? So we probably don't want to do, then we probably cannot do sorting. If we cannot do sorting, what other approaches can we take that would use O of n log n time? O of n log n time. Maybe we could do some sort of binary tree traversal on it. So we turn it into a binary tree in some way, and then we traverse through it in order to get the longest increasing subsequence. But that would still involve some component of dynamic programming, because we'd still need to keep track of what's the longest increasing subsequence that we've seen at a particular item, right? I'm genuinely unsure as to how we could approach this in O of n log n time. But a binary tree typically does get us closer to that, in a similar way that a heap would bring us to O of n log n time, as in the previous problem. But I don't think that a heap is necessarily what we want in this problem. Sorting algorithms, in the average cases, would bring us to O of n log n time, but we need to preserve the order of the sequence, so therefore we should not modify the array in that way. That would change the ordering of the elements, essentially. And yeah, if we sorted in an array, then the longest increasing subsequence would probably change pretty significantly, now that I think about it. Yeah, it changed very significantly for arrays that have strictly increasing values. So sorting is out completely. So that leaves sort of binary trees. We could also attempt to do some sort of quick select, but I don't think quick select is what we want here. Quick select is usually for like frequency of elements. That would be like k closest element, k something element, right? And here we want to just optimize. We don't want to get the k whatever. And we need a sequence which cannot be changed. So kth style approach with quick select is out. And quick select, in case you aren't aware, is just the essentially partition part, the partition phase of the quick sort algorithm. And the idea is that if you partition elements, then you know how many elements are on the left and how many elements are on the right, and therefore you know roughly the position of the element in terms of the largest or smallest that your element currently is. So it's a little bit faster, I believe, than heapifying. Where heapifying and getting that element is O of n log n time, the quick select is O of n time. Well, is it? I think so. I think like in specific cases, like you can get it to roughly of um, linear time, though there are some caveats there as to like sort of your partition and things like that. But that's not the answer here. I don't think so. We can deal with quick select when it comes up in another problem. Tell you what, I'm going to code out the dynamic programming approach since it's more like the sort of traditional approach, and then we can come back and think about this a little bit more. So let's start with creating our array. We'll say val longest chain array is equal to an int array of size num size, where every element is initialized to 1. Because of course the longest chain is 1 at the beginning, because every element can be the start of a chain. And then we can say nums for each index num, and then we can say var max so far is equal to 1. We'll say max chain so far. And then we can say for I in 0 to index minus 1. If nums at I is strictly less than num, and the longest chain array at num, or at I, is greater than the max chain so far, then the max chain so far can be reassigned to the longest chain, or well, this is plus 1, array at I plus 1. And then after that, we can just say longest chain array at index is equal to max chain so far. And then let's see. We can further optimize this by also creating a variable max chain scene total. And we can say if longest chain or max chain so far is greater than max chain scene total, max chain scene total is equal to max chain so far. I know these variable names, as expressive or as verbose as they may be, are probably not entirely intuitive, and I ask for your understanding on that. But anyways, so we create a longest chain array, which keeps track of if we were to cut off the array at that point, and we wanted to know the optimal answer for that element, what would it be, right? And that's our dynamic programming part, essentially. And so we have a set of subproblems, essentially, where we go through and we check to see, okay, is the number strictly less than our current number? And if so, is their chain plus 1 larger or longer than the chain that we've had so far, which defaults to 1? And if so, then we will set our max chain so far to that number plus 1. And then at the end, we will assign our variable at our index, at our current index, to the max chain so far. And if that's in total, in aggregate, that's the longest that we've seen so far, then we'll add it, or we'll set it to our maximum, and then we'll return that maximum. Again, this runs in O of n squared time, and we're looking for, in our follow-up, we're looking for an approach that runs in n log n time. But let's first check and run our code to make sure that there aren't any issues. And let's go ahead and toss in a submit to see the speed of it. Probably wouldn't be entirely fast because we know that there is an n log n time complexity problem. Sorry, an n log n time complexity approach. Though this submission seems decent, but let me think. How could we do this faster? Union find? Wait, is this a union find problem? So if we set every element to its own self, then we start connecting the chains and we do the sort of crushing part, would that give us an O of n log n runtime? Is this actually a union find problem? Because then that chain would give us the longest let me think. But how would we... I'm just thinking of sort of how would we do this? Okay, let's suppose that this is union find, because I think that this is a union find problem. I think it makes sense because we have a bunch of somewhat disconnected components, but also somewhat connected components. So start each element as its own chain. So we have, like, for example, 0, 1, 0, 3, 2, 3. Then for each element within the chain, find how would we want to do this though? If we, because we want to maximize the length. So if we start with 0, what would we realistically want to do there? Like, maybe we keep an additional element within because if we don't break down the chains, if we don't keep the chains as they are, if we like sort of compress them in the way that makes the union find actually efficient, then we sort of lose the context of like whether or not we have a value that we can slot in, right? But it feels like maybe it would work. But I'm really not sure. This is... I'm not very familiar with union find. Is there another way that we could accomplish this then? Is there like some like obscure algorithm that I'm aware of, or maybe this is just obvious and I'm not getting it? At the same time, I know that union find is like bordering on like the realm of like something that may not necessarily be common knowledge. I think the realm of common knowledge is stuff like dynamic programming, ironically enough, greedy problems, divide and conquer, and then graph-related problems like simple graph-related approaches like breadth-first search, depth-first search, and then the various tree traversal algorithms, so post-order, in-order, pre-order. Set that out of order, but It's fine. So those are like sort of the common knowledge algorithms questions that I expect a lot of. Um, O of n log n and union find. Really not sure. So let's say that we wanted to do something like that, right? So if we found like a 10, let's say that we store 3 variables within the node. We want a root or a parent, which is a node. And this, of course, will just be the parent of our current node. We want a value, which represents our current integer, and a min, which represents the minimum integer that currently exists within our chain. So the idea of the minimum is basically to check to see if this can slot in as the last element within our chain. A candidate node can fit as the last node within our group. But again, we lose a lot of context if we want to compress it. Because I think the only way to get an n log n runtime is to compress the union find tree so that it's not as tall and it's more wide. But how can we get that? If we... Because then we have to check all of the elements, right? And that would be no good. Because the idea is that if we wanted to add an element slash merge two components together, we'd first compare the roots to see which one would merge into which. Then we'd say compare or see if we can even fit the elements, or rather where the elements fit in. Maybe in that case we just have like a set of nodes in the root and check the intersection. And the idea is that as long as there's no intersection, then we don't need to worry about it. Like, so say we had 2 roots where one is larger than the other. If we check the 2 intersections and there is no overlap between them, then we can safely say that all the elements within the smaller group can probably fit within the larger group. And since there is no intersection between the children, or really the descendants, then we know for sure that they can just fit together, right? That no matter what, they can sort of slot together. And that sounds a little bit more reasonable. I think that makes sense, right? Suppose we had 2 components with roots A and B. If A is less than B, and A dot set intersect B dot set is equal to null, then we know that for each element within B, or within A, no element exists as a descendant of B. And furthermore, since there is no overlap and A is the largest element within the set, within A.set, then all elements would be able to fit within B.set. I think that makes sense. Coding this up would be a bit of a nightmare though. But okay, let's see if that works. Let's suppose that this just magically works, right? Let's just black box it. And let's say what would happen afterwards. Then in that case, set A's parent node to B and set B's set B.set to A.set union B.set. And this is assuming that everything has been compressed so far. So 3a, if the elements, or if the nodes are not compressed, we need to do so in order to have a faster runtime. And we'd have to compress it further. I think this approach might work, and it might give us the runtime that we want. So we need to compress the nodes. And that gives us the advantage of the wider tree versus the taller tree. When we set the parent, do we need to change the set? No, we shouldn't need to change the set. All we really need to do is to change, because the set doesn't affect, isn't affected. Only the parent node is affected. Interesting. So in that case, we do something like for 0, we'd merge with 1. So now 1 is the root. And then we'd merge with 3. So now 3 is the root. And none of these make sense. Then we have 0, then 2, or 0, which would not merge with this 3, because this 3 has a 0 in it already, so it wouldn't merge there. And you merge with the 2, and you merge with the 3. And this 2 now Yeah, I'm really not sure how I would be able to do this in a faster manner, even with union find. It seems like you would need to also consider like the route that you're merging with to be the most optimal, which might work, but maybe union find isn't the answer. Maybe I just went on this weird rabbit hole of a adventure, but it's exactly 30 minutes now, so I'm gonna take a look at the optimal answer, and we'll see. I'm not gonna lie, this one is really weird. Okay, so apparently it's based on something called patience sorting, which is a sorting algorithm that is based off of a card game, I guess, called Patience. The idea, I think, now is a little bit more understandable and a little bit more clear to me. The idea is that you have these piles that you start off with, or, well, you start off with 0 piles. The first card, or the first element that you see, you put down and you create a new pile. And basically, for every other card you check, you scan through all the piles and see if there is a place where the card is greater, and you can place it down there. Right? So if the card at the top of the pile is greater than the card that you're holding or the element that you want to insert, then you add it to the pile. And this essentially gives you the longest increasing subsequence within an array. So how did this translate into code? Well, I took this solution from Sithis and translated it into Kotlin, simply because I felt like their comment on sort of what was going on made a lot more sense to me than the initial solution that was posted in the original post. So we start off with the same idea of the piles, right? And we create a mutable list of and we then check. We check within our list using binary search, which is why we have the log n time within the O of n operation, to see if there is a place where we can insert, or rather, we'll get back to that. We run a binary search. There are two main outcomes. The first outcome is that we don't find our element within our list. But if we don't find our element within the list, however, we do know, based on the way that Java's binary search works, the index of where it should be if it were inserted in the array. This is given to us as the negative of the insertion index -1. So the insertion index is defined in Java as the first index where the key is larger than our current value, right? So if we're looking for example, a 3, that insertion index, assuming that there are no other 3s within our array, because then it would be found, right? That key would be the index of 4. Well, the negative of index 4 -1, which if we invert it using a bitwise not, then we get the actual insertion index, because 2's complement? Maybe 2's complement. So that defines where we should put the card. And the idea behind that is that when we do run this 2's complement inversion thing, well, we're given the place where we would insert that card, and of course we did not find that card within our array. So in that sense, that position of that pile, we can set it, we can add to it, we can put our card on top of it, because we know that that insertion index is the index of the first index that is larger than the number that we want, right? So we know that number is larger than what we want. We know that our index currently doesn't exist within the array, so we can set it onto that pile. If a pile does not exist, then of course we will just add to the list, right? So that's the end here. And this is the idea that if we scan through all the items within our piles, and we do not find a pile that has a smaller top number, then we'll create a new pile with that one as the bottom, or the top, I guess. And this essentially creates a structure where we can, well, get a bunch of these piles, and slowly start moving them down, essentially moving them down, essentially starting from the largest numbers, and then slowly piling cards on, assuming that they match the sequence. I'm still not really too sure about how this works in its entirety in terms of how this actually gets us the longest sequence. It does make sense within some context, and I guess with respect to, for example, like it's a lot more obvious for something like this example 3, where if you have a 7, so the first 7 you add to the list, right? Then the second 7, well, it already exists within the array, so you just set it, and you just keep on setting that array, so your list is only growing to size 1. So I guess the idea is that as you move left to right, because we are moving left to right, we are guaranteed that this sequence will hold left to right. And when you keep adding to the end of the list, you are guaranteed in that sense. So you either add to the end or you add to the beginning, right? Or you add to somewhere in the middle, rather. So when you add to the end, you are increasing the longest common subsequence. And you know that because we're moving left to right, okay, this is starting to make sense once I actually talk this out. When you add it to the end of the list, and because we're moving left to right, we guarantee that this will maintain the subsequence invariance. And because we're adding items, if we have an item and it belongs somewhere within the middle of the subsequence, we just reset it, right? So this, if there is a longer subsequence that exists within our array, we'll override all the middle items within our subsequence, and then we'll add on to it at the end. Okay, so this is actually starting to make sense now. This is really cool, but at the same time, I don't know if this is really applicable anywhere else, but it's a really, really interesting algorithm. Probably something that you could bring up with your interviewer, but probably something that, well, I hope they don't really expect you to know this one obscure algorithm. I mean, like, I know that some people say that even Dijkstra's is an obscure algorithm. I disagree with that, but this algorithm, I think it's a bit more obscure. In any case, so that's the patience sorting algorithm, and it's honestly about the same, but that could be chalked up to just LeetCode being LeetCode. It's definitely an interesting algorithm, and it's very easy to justify the runtime. It's just not as easy to justify its correctness. That took me a while to get. I'm still not sure if I really quite fully grasped the idea, but I think it's cool. And I'm starting to get it, right? The idea of the left to right, adding and resetting the sequences, I think that all seems to make sense to me. In any case, I hope you learned something, and I'll see you for the next problem.